Welcome to the final edition of Comet Algebra for Chapter 9. For Chapter 9, I know you're very sad to see it end, but all good things do come to an end. So 9.6, graphing rational functions. Now this is different than reciprocal functions that we did in 9.5. With rational functions, we have a numerator and a denominator that are both polynomials. So of course there's factoring involved, a little more work. Let's start by looking at this example of x minus 3 over x squared minus 2x minus 3. I would like you to graph that on your calculator. The graph on your calc screen should look something like my sketch. And I just want to point something out. This graph does have 2 points of discontinuity. It does have an asymptote and it does have a hole in the graph. But how do we find them? And of course we talked about this in the last video. You cannot see this hole in the graph on your calc screen. But I know it's there, so I'm pointing it out to you. So that's the first part of our lesson. Looking at our denominator here. This denominator is going to give us 2 things. It's going to tell us the vertical asymptotes, and it's going to tell us if there's any holes in the graph. And we have to determine which ones are which. And so this next part of the notes is how to identify them. Okay, once again to review the points of discontinuity. Anywhere that the denominator is 0 is a problem. It's either going to be an asymptote or a hole. So first we need to find all the values where the denominator is 0. And then we have to do some comparing. So I took our example and I went ahead and I factored the denominator, and this is what it looks like. So we have 2 points of discontinuity. We have a positive 3 and a negative 1. The vertical asymptotes, it says here, are found at any 0 of the denominator that does not have a matching 0 in the numerator. So if we look, I'm trying to kind of do our example at the same time here. So if we're looking for a vertical asymptote, it's a 0 that does not have a match. Okay, this 0 of 3 has a match, so that's not a vertical. This 0 of negative 1, there is no match of that same binomial in the numerator, therefore this is a vertical asymptote. So a vertical asymptote would exist at x equals negative 1. And then reading number 2 here, a hole in the graph is found where there's a 0 that does have a matching 0 in the numerator. So since this x minus 3 has a match here in the numerator at that x minus 3, therefore we do have a hole in the graph at x equals 3. So take a minute and write down these 2 important details about vertical asymptotes and holes. And then in a moment we'll discuss how to find the horizontal asymptotes. So the horizontal asymptotes are a little different in these rational functions than they were in the previous section with reciprocal functions, because we don't have a value tagged on at the end here. We don't have like a +4 or something where it's very easy to look at and find the horizontal asymptote. So it's a little more complicated. To find them, we need to look at the degrees of the numerator and denominator and compare them. Now, just to help you refresh your memory, a degree is the highest exponent. So first of all, rational functions, they're either going to have one horizontal or they're not going to have any at all. So those are our choices. Again, to find them, you compare the degree. If the degree of the numerator is smaller than the degree of the denominator, then we have one horizontal asymptote, and it is at y equals 0. So those are sort of the easy ones. Second scenario could be that their degrees are the same, that both the numerator and denominator have the same degree. Then we use what's called the leading coefficients. We write the horizontal asymptote y equals whatever the leading coefficient is of the numerator over the leading coefficient of the denominator. And then we just reduce that fraction if possible. Now this one is the weird asymptotes. When the degree of your numerator is larger than the degree of the denominator, there isn't a horizontal asymptote, but there could be what's called an oblique asymptote. But in class, you guys seem to prefer me using the word slanted. So sometimes the asymptotes aren't exactly horizontal or vertical. They could be a slanted line. And the way we find the equation of those slanted asymptotes is we need to complete the division of the denominator divided into the numerator. So our division of polynomials comes back. I think we need to review both the synthetic and the long division to help us with this. So I'd like to look at some examples. In example 1, we're asked to identify the asymptotes, both horizontal and vertical, and to graph it. So I started drawing the graph over here. It has the two pieces in blue here, and then the middle piece of this looks like an upside down parabola. So we end up with a three-piece graph. So by looking at it, I know I'm going to have to find two vertical asymptotes and find this one horizontal asymptote. So I start by factoring anything I can, both numerator and denominator. The denominator is the difference of two perfect squares, so it factors into conjugates, x plus 3, x minus 3. And now we just know we have to know how to read the clues that were given. So first of all, the points of discontinuity. We have a problem here in our denominator. We have a problem at -3 and +3. So those are the first, my thought is points of discontinuity. And we need to decide, are these vertical asymptotes or are they holes in the graph? If they're holes in the graph, there would be a match for these binomials in the numerator, and neither one of them have a match. So I'm left to conclude that these are both vertical asymptotes. So I have a vertical asymptote at x equals -3 and x equals +3. And looking at the graph, that is certainly the case. I drew in these vertical asymptotes as dotted lines. Then we need to shift gears and look at the notes we had for horizontal asymptotes, where we compare the degrees. The degree in the numerator is 2, the degree in the denominator is 2. So we have a case where they are both the same. So look back at your notes where it says same, and it says there is a horizontal asymptote, and it is found where y equals the leading coefficient of the numerator over the leading coefficient of the denominator. So what leading coefficient means, it's the highest exponent, and we look at the number that's attached to that. So both of them, the highest exponent is the x squared. This leading coefficient in the numerator is a 3, so I use that as my numerator. The leading coefficient in the denominator is 1, so it's 3 over 1. Therefore, my horizontal asymptote is at y equals 3. And that completely fits with what I'm seeing in the graph. In this example, we're asked to identify all the asymptotes that we can find and find the intercepts. Intercepts means where does it cross the x-axis and where does it cross the y, and graph it. So we're going to start by factoring both numerator and denominator, and if we inspect them, we realize, I hope, that there is a GCF for both of them. And we know that when we take out the GCF, our factoring becomes much easier. So factoring the GCF out of the numerator and denominator, And then factoring the trinomials into the two binomials leaves us with this completely factored form of both polynomials. So to identify asymptotes, we first look at the denominator and ask ourselves, what are the points of discontinuity? Where are we going to have problems? And here we have a 0, a problem at 2, and here we have a problem at 1. So we got to check both of those values. These could be vertical asymptotes or they could be holes in the graph, depending on if there's a match. So we look here, we do have a match of x minus 1 in the numerator and denominator. So we can conclude that that is a hole in the graph at x equals 1. This x minus 2 does not have a match in the numerator, so we know that that is a vertical asymptote at x equals 2. So the next thing to check for is horizontal asymptotes. And we know that we need to compare the degree. So going back to the original here, we notice that we have a third degree in the numerator, so that degree is greater than the denominator, which has an x squared. So looking at your notes, when it's a greater degree on top, we do not have a horizontal asymptote, and we have one of those oblique asymptotes or slanted. So at this point, I think it would pay to stop and enter this on our calc and graph it and take a look at it. All right, I tried to show in my sketch the information that we know so far. I drew in the vertical asymptote in red here at x equals 2. I attempted to make a hole in the graph at x equals 1, and then we have two pieces to this hyperbola. And in my sketch, this isn't going to be very accurate, but I'm suspecting that there's an asymptote running somewhere kind of like that. So that's what's known as an oblique or slanted asymptote, and that's what we need to find. And the way we find that is by completing this division right here in the original. We have to divide that denominator into that numerator. And like I said, you can use long division or synthetic. But in this case, we can't use synthetic because we don't just have one factor on the bottom that we're dividing by. So this one has to be long division. All right, here's the long division set up. So just to review, we ask ourselves, what can we multiply this 2x squared to get an x cubed? Well, to get rid of the 2, to get that to a 1, I need a 1/2. And to go up to an x cubed, I would need another x. So multiplying 1/2 x times 2x squared would give me x cubed. Then half of 6 is 3, so that would be a minus 3x squared. And half of 4 is 2, so that would be a plus 2x. And then if you remember, we change the signs and add, so this becomes negative, positive, negative, and we add. And remember, our goal is to make this first term add to 0. So now I have negative 2x squared plus 2x, and bring down my placeholder of 0 there. And then we ask ourselves, what did we multiply by 2x squared to get a negative 2x squared? And that would just be a minus 1. And then distribute that negative 1. Plus 6x minus 4. Change the signs and add. And here's what's really nice about this process. Even if you get a remainder, it doesn't matter. This part here is the equation of this slanted asymptote. So our oblique asymptote right there is y equals 1/2 x minus 1. All right, next, just a quick review of finding the intercepts, or where it crosses the axes. The y-intercept is where x equals 0. So putting in a 0 into the original there, I would get 0. So I'm finding f, better write this out, f of 0. 0 cubed is 0, minus 5 times 0 is 0, plus 4 times 0 is 0, all over 2 times 0 is 0, minus 6 times 0 is 0, and then plus 4. So therefore, 0 over 4 is 0, and that's where we have our y-intercept. So the y-intercept would be at 0, 0. And next we need to find our x-intercepts. And the x-intercept is where the value of this is 0, but we have to be careful, or y is 0, but we cannot end up with zeros in the denominator. So a good way to say that is the x-intercept. Wherever there's x-intercepts, these are zeros of the numerator that do not have a match in the denominator. So looking at the factored form, we want to find zeros in the numerator without a match. So this x minus 1 and x minus 1 is a match, and of course we know that's where our hole in the graph is. So let's look at these other two zeros in our numerator. If x equals 0, x equals 0. If x minus 4 equals 0, x equals 4. So those are our two x-intercepts. So just to state this, we have x-intercepts. It crosses at 0, 0 and at 4, 0. And then we have a y-intercept at 0, 0. And I believe we stated earlier that we have a hole in the graph at x equals 1. All right, I think that's it for section 9.6. Have fun.